Hello, welcome to the last and fourth A-level session. Today's session will be on integration and your presenter is Mr. Mackenzie.
Hello all, as we said, this is the last one on integration. We've tried to sort of put as many different forms of integration in there, and it's leading on from last session on partial fractions. We've got integration by parts, substitution, and with a little bit of trigonometry, and finally with differential equations where you split it. So let's get started as there's a lot to do. I thought what I would go through first of all is if you have a look at these are sort of basic integration just to make sure that you're happy with them. The first one is an exponential. So with the exponential, if it was just e to the x, you would expect this to just go to, oops, sorry. My pen seems to be, no, there you go. Let me rub that out. Pen. So if this is e to the x, you would expect the integral of this would be e to the 5x over 6. However, if we were to differentiate this, we've got a constant, so we need to account for that constant. So because if we were to differentiate, we would have 5 over 6 e to the 5/6x. What we need to do then is flip it so that when we differentiate it, that powers, the 5/6's would cancel with 6 over 5. And then we would need to make sure that we put that plus c in there. So that's going to be a plus, a constant in there. It's the same thing. It's almost like the reverse of the chain rule where you've got to be thinking about it. Okay, so sine would go to minus cos. So we're going to have a minus cos of what's inside, which is going to be 1 minus x over 3. Don't forget that plus c. But we have to take into account what's inside with the cos. So here, if we were to sort of differentiate this, minus cos would go to minus sine, and it stays inside. It's the same thing stays inside, and then that would be minus a third outside. So to counteract that, we would times this by minus 3. If I put a massive bracket around this. And then when we multiply it out, this is going to be 3 cos 1 minus x over 3, and then it'll be the plus c. And then finally, this is the one which is going to be the one that's going to be most used with when we're doing partial fractions because of the value underneath. Okay, so the x term is underneath. So because it's going to be underneath, you're going to, it'll be 1/6x minus 3 to the minus 1, and what I'm hoping you've seen with this before is that it turns into a log of 1/6x minus 3, and then we've got to deal with this 5, which is already there and is a constant. And not only that, if we were to differentiate this using the chain rule, you differentiate inside, so there's going to be 1/6 log 1/6x minus 3. Well, that's 1/6 too big, so to counteract that, we would put a 6 there. So when expanding this, it would become 30 log 1/6x minus 3 plus c. Another one which I haven't put on here, and I'll change color for it, which comes up quite a relative. Sorry, the color, which comes up every now and again, would be if you had the integral. And say you've got an x there, and then the bottom you've got x squared plus 3 dx. Okay, it's important that we put the dx because we're integrating with respect to x. What I'm hoping you can see is if on the bottom here, if I differentiate it, I'm going to get a 2x out. So what I think is going to end up looking like is, because it's all to the power of minus 1, it's got to be a log. So it's going to be x squared plus 3. Now, differentiate this, you get the 1 over x squared plus 3, and using the chain rule, we have to differentiate inside. So that's going to be 2x over x squared plus 3. This is very similar to this one, but it's too big. So therefore, you cut it down by half, and then plus c. So those are sort of basic ones that we want to go through. Now, this question was all these are taken from different exam boards and different exam papers, I didn't want to go through the partial fractions because Ms. Pritchard went through it last week, and if you need any help on that, then I'd suggest you go back. So I've just basically put down the answers where if we put it as a over x plus 3 squared plus b over x plus 3 plus c over x minus 1, then the answers out were a was equal to -7, c was equal to 2, and b was equal to 0. So the part A of the question was to express it in partial fractions. And then part B is now we have to integrate it. And I thought what I'd do is I'd put the limits in as well so that you can see what you need to do with the limits. So it is between the limits of 10 and 3. And then give your answer correct to 2 decimal places. So the integral of f of x, so this is going to be between 3 and 10 of -7 over x plus 3 squared, and then b is gone, so I mean we can cross that off because b is equal to 0, and then plus c, which is 2 over x minus 1, and that is integrated with respect to dx, or respect to x. The -7, because it's got the powers on the bottom, I prefer to sort of bring them up. So if we rewrite that out, that's why the next one is a blank page, so I've got more room. So it's going to be -7, and then it's x plus 3 to the -2. And then this is plus 2 over x minus 1. We know that this is going to turn into a log, so I'm not going to bother or worry too much about it there. And again, it is between the limits of 10 and 3. So if we integrate the first bit, and we always put a square bracket, this again, so we are increasing the power by 1, and we're dividing by the new power, and we have to also take into account if there's anything. Luckily, there's nothing inside the bracket that's going to affect this, because when you differentiate inside, it's going to be a 1. So we don't have to worry too much about that. So we've got -7, and then it's going to be x plus 3 to the -2 all over -1. And then the next one is going to be 2 log x minus 1. This time we don't put a plus c. Okay, the reason why we haven't got a plus c is because we're going to have the exact answer to this. If you remember, integration is looking at the area underneath the curve between the x-axis and wherever the curve is. So this is, as I said, when you see a next question, you'll see what I mean by that. So once we've tidied this up, I put -2 there, sorry, it should be, that should be -1, I even said -1. So then once we tidy this up, the -1, we're having the 2 minuses cancel, so we have 7 over x plus 3 plus 2 log x minus 1. And as I said, it is between 10 and 3. So on the next page, we just fill in for the different values between 10 and 3. So it's going to be 7 over 10 plus 3 plus 2 log 10 minus 1. And that then is take away 7 over 3 plus 3 minus 2 ln 3 minus 1. Tidying that up, that becomes 7 over 13 plus 2 ln 9 minus 7 over 6. Now that minus, that should be a plus there, sorry. So that becomes minus 2 ln 2. Hopefully you can sort of remember with logs that 2 ln 9 is the same as ln 9 squared, which is ln 81. Okay, just because I want to tidy it up. And also, if you think that this is 7/13 minus 7 over 6 is minus 49 over 48, sorry, 49 over 78. And then if we deal with the logs, so we've got plus ln 81 minus ln 4. So then I can write this as one of the the sort of division rules of logs. So the 81 would be divided by the 4. So ln 81 over 4 minus 49 over 78, and that is equal to 2.38. Next one, just a couple of rules of logs there to go with it. So here we have what I mean by the purposes of integration, where it's the area under the curve. Now, remembering that if it is above the x-axis, that area would be positive. If it's below the x-axis, which is what this part is asking us to work out, that area, when it comes out, is actually going to be negative. So then you're going to have to flip it to make sure then you've got a positive, because you can't have a negative area. So again, I've I've preempted this question, and it says the diagram shows that part of the curve y equals 2x minus 1 over 2x plus 3 x plus 1 all squared. Find the exact area of the shaded region given your answer in the form p plus q log r, where p and q are positive integers and r is a positive rational number. So there's a lot going on here for the 10 marks. Now, as I said, up the top here, I have already sort of written out what the answers to the partial fractions would be. Saves us sort of going through it, and if you need any more on partial fractions, go back to Mrs. sort of earlier webinar. So we have here, we need to find out that value. So we need to find out where, we need to find out where there it is sort of equal to. In doing so, that's where this graph crosses the x-axis. Therefore, y is going to equal 0. So if we take the original equation, y equals 2x minus 1 over 2x plus 3 and x plus 1 all squared. If we put y equal to 0, then all of this will go over to the other side and will also be 0. So we're left with 2x minus 1 is equal to 0, 2x equals 1, x is equal to a half. So when we sort of write out this, the limits are, because that's where it goes from 0 to a half of the above. So it is minus 16 over 2x plus 3 plus 8 over x plus 1, and then minus 3 over x plus 1 all squared, and that is dx. So now that I'm going to rewrite it, I know that this is going to be a log, I know that this one is going to be a log, and I know that this one is again going to be minus 1, okay, because the power is 2 on the bottom, so when you bring it up it's minus 2. You increase the power, it'll go to, excuse me, the minus 1. So again, the limits, square brackets down, I've got minus 16 log 2x plus 3. I need to sort of deal with that constant there, because if I was to differentiate, I'd have 1 over 2x plus 3, and then I'd have a half outside. So to counteract that half, I'm going to have to times so I'd have, let me see, ln 2x plus 3. If we differentiate this, it's going to be 1 over 2x plus 3 multiplied by inside, which is 2. So because I've got that 2 there, I will have to, where's the rubber? I'll have to divide this by a half, because then it's going to be too big, because I don't want that 2 on top. And then I've got plus, this is not going to help me with anything, it's x plus 1, so it's just going to be 8 log x plus 2. And then this, as I said, if I was to rewrite it, and normally I rewrite it on the top above it, so I don't have to sort of waste space, so it's going to be 3x plus 1 to the minus 2, so that when I do work this out, I know that it's going to increase the power. So I have got, if I write it as minus 3 x plus 1 to the minus 1 over minus 1, and again the limits are between 0 and a half. So what we end up with is minus 8 ln 2x plus 3 plus 8 ln x plus 2 plus 3, and I'm going to stick it underneath x plus 1, 0 to a half. Now we need to put in the values. So we've got a half going in, half of 2 times a half is 1 plus 3, so I'll give you the 4. A half plus 1 is 1.5, and then the last one is also going to be 1.5. So if I just square bracket these, so we would have minus 8 ln 4 minus 8 ln 4 plus 8 ln 3 over 2 plus 3 over 1.5, and then we're going to stick 0 in, so it's going to be minus 8, 2 plus 3, 0 goes in, so it's just going to be 3, and then 0 plus 1 is going to be 1, and log of 1 doesn't exist, so we're going to have that as minus 8 ln 3, and then the last one is going to be 3 as well. Tidying it up, we would have 8 ln 3 over 2 plus 2 minus 8 ln 4 minus the minus, that's going to be plus 8 ln 3, and that's going to be minus 3. With the logs, we can take 2 and the minus 1. So if we take these two first of all, then it's going to be 8 outside ln 3 over 2, and that's going to be divided by the 4. So then it's basically 3/8 on the bottom, and then the 3 comes in, it's going to be times. So if I put like that, so it's going to be then times 3 on the top, and then it is going to be minus 1. So then simplified, this is 8 ln 9 over 8 minus 1. However, the issue we've got, we were originally told that the integers had to be positive, and this is underneath the graph. Because it's underneath the graph, I will, to work out the area now, so I've done that, I'm going to work out the area. So multiply by minus 1. So I've now got minus 1 times 8 ln 9 over 8. Sorry about that. Let's try that again. 9 over 8. The pen seems to be jumping about a little bit. That's not going to work. Hang on a second. You love computers. Okay, hopefully that'll work. Minus 8, and then that's going to be minus 1. That is not. Let me erase that, and then hopefully if I take out my pad and then put it back in, it will then work. Maybe if I just take out the mouse. Pen. So as I said, minus 1 times 8 ln 9 over 8 minus 1, so that the area is equal to minus 8 ln 9/8 plus 1. Again, we haven't got a positive integer, but we can put this to the power of minus 1, so that we have 8 ln 8 over 9 plus 1, which is answering the question. The second question is integration by parts. Okay, so here you have a function multiplied by a function, and then when you're integration by parts, you take one of the functions and you differentiate it, so to make it easier, and you take the other function and you integrate it. So you treat one as u, v minus the integral of v du by dx dx. You always, what you're trying to do here is to make the function that you've got that little bit easier. So if I was to sort of Integrate x to the 4, that's just going to increase the power. It's not going to help me at all. And I can't, unless I do integration by parts, integrate log. So what we do is we take u, which is the one we're going to differentiate, which is log 2x, and the v is going to be x to the 4. Sorry, dv by dx is x to the 4. If we differentiate logs, we get chain rule, so 2x goes to 2 over 2x, so it's going to be 1 over x. And then if we integrate this, it's going to go x to the 5 over 5. And then this is the formula that we use to use integration by parts. So it is uv minus the integral of v du by dx. So my uv is, so this is then equal to x to the 4 log 2x minus the integral of v, which is x to the 5 over 5 times 1x. So x to the 5 over 5 times 1 over x. And then again, this is with respect to x. That will cancel, so that's now x to the 4 over 5. So when I write it out, it's going to be x to the 4 log 2x minus integrate x to the 4, so it's going to go x to the 5 over 5 times 5, which is x to the 4 log 2x minus x to the 5 over 25, and then I want to put a plus c there. Okay, that is plus a constant, and instead of an equal sign, we're going to put an arrow, so that it's not obviously with a plus c. That's because it's definite integral and we haven't got the limits. In doing that, you could have put a plus c further along. I mean, here we've integrated it, but then what happens is you just change it to a plus k. So what I do with my constants, I wait until the very end and then I do it, put a plus c in rather than sort of intermediately throughout. The next one is also integration by parts, but this time you're going to have to do it twice. The reason why, there is a third one which I haven't done because it's not in the syllabus, where you integrate it twice and the last function is actually the original. You have to do a sort of bit of maths jiggery pokery to get what you need. So here, e to the x just goes round and round as e to the x. So whether you integrate it or differentiate, it doesn't make any difference. If you choose to integrate x squared, you're increasing the power every time, so it's not going to sort of do anything there either. So with this one, what you would have to do is you choose u as x squared, so that when you differentiate it, you get 2x. So you've reduced it down. Okay, I realized that we're writing a little bit too big, so let me highlight that, get rid of that, so that I can fit everything in. So then du by dx is 2x, so dv by dx is equal to e to the x, and then when you integrate it, it is just e to the x. This is equal to, from the other page, it was uv, so it is e to the x squared minus the integral of v du. So it's going to be 2x e to the x dx. As you can see, we've reduced the power on the x squared, so it's a little bit more manageable, but we still can't integrate it straight away. So we would then do u dash or u1 equals 2x du1 by dx equals 2. And then again, we would do dv1 dash or dv1 by dx, and that is equal to e to the x. So v1 is e to the x. So then this equals e to the x squared minus, and I'm going to put a square bracket around here because it's going to be u1 v1. So it is 2x e to the x minus the integral of v1 du1 by dx. So it's going to be 2e to the x dx. The reason why I put a square bracket is because of that minus sign there. And then when we integrate this, this is just going to be 2e to the x. So it equals e to the x squared minus 2x e to the x minus, and a minus is a plus, and that would go to 2e to the x, and then I'm going to put a plus c. What I also hope you could notice is what's common to all the terms is e to the x. So if they were asking you to sort of look for something else, you can clear it up as x squared minus 2x plus 2, and then obviously you put the plus c there as well. Integration by substitution. Okay, I'm sort of aware of time, I'm trying to get through as much as possible. So if we have a look at integration by substitution, majority of the times they will give you the substitution, okay, because it is quite difficult. If they don't, then you're going to have to look at wherever's on the bottom or wherever's side by side. If it's the differential of two functions, if one function is the differential of the other, then you choose the one, because when you differentiate it, you sub it in, it'll cancel out. What I mean by this is here you've got x cubed. Don't worry about the signs because you can deal with them as you go along. If you differentiate x cubed, it becomes x squared, which is on the top. So that is why you've chosen what's on the bottom. So, and I will do the limits on this one, but I probably won't do the limits on any other ones. You've been told that your integral substitution is u equals 12 minus x cubed. If you then put that in, you've got x squared over u squared dx. Okay, in the original function, there's all x's and you're integrating with respect to x. That's what that dx stands for. You now put u in there. So you've got a mixture of two unknowns and you're integrating with respect to x. You can't do that. So you're going to have to change that dx. And how you do that is you go back to your original things that you're putting in as a substitution, and then you differentiate it. So you do du by dx, which is equal to minus 3x squared. Rearrange, so du over minus 3x squared is equal to dx. So now this dx here is going to be replaced with this dx here, which is du minus 3x squared. Integral, so you've got x squared over u squared times du over minus 3x squared. That 3x squared will cancel with that one. You can move the number outside because it's a constant, so it's minus 3. The integral of u to the minus 2 du. Now you've got your one unknown instead of two, which is a u, and you're going to be integrating with respect to that u. That du means that. So if I put a line down here, so I've got space. So then you would increase the power. So this is u, let's put minus a third, and then it's going to be u to the minus 1 over minus 1, which is going to be equal to, let's see, 1 over, and then that minus 1 comes down, they cancel out, so it's going to be 3u. You can either substitute back in that u if you wanted to, or what you could do is, where am I looking at? If you wanted to, you could then change the limits. So you could either put this as 1 over 3 and then open brackets 12 minus x cubed, or you could change the limits of the 0 and the 2. In changing the limits, I'm not going to put them in, but I'll show you how to change the limits. That way then I can move on to the next question. You use this function and then you say, well, x is equal to 0. Then u equals 12 minus 0, so it is equal to 12. So that's the lower limit. When x is equal to 2, u equals 12 minus, and 2 cubed is 8, so that's equal to 4. So what I should have shown you here is when you put the limits of 12 and 4 in, I've got a minus outside and it doesn't look right. So what you would do is you would flip the limits and change and multiply the sign by a minus. So you've actually got 1/3 for 12 u to the minus 2. So then this becomes minus, because originally we got rid of the minus signs here, but I should have got rid of them further back. Pen. So then that minus stays, and then you would stick in your limits between 12 and 4. So it is minus 1/3 times 12 minus -1/3 times 4. And then you can sort of put that straight into your calculator and you end up with 1/18. Okay, the next slide, again, they're giving you the substitution, and we're trying to sort of do a little bit of trig with this as well, so there should be some trigonometry. So we have u equals 10 cos x minus 1. So with u equals 10 cos x, we do the usual thing of differentiating it. So du by dx equals 10 cos x minus 1. Differential of cos goes to minus sine, so this is going to be minus 10 sine x, and the sort of minus 1 just disappears, so that we can write this as du over minus 10 sine x equals dx. I'm not going to do the limits because you can just put them into the calculator and then I can get on. So then this is going to be the square root of u sine x, and instead of dx I'm now replacing it with du over minus 10 sine x. Again, you can see that that sine x is going to go. I'm going to move the minus 10 outside of the integral, and then that's going to be u to the half du. If we got u to the half du, then that is going to go to minus 10, sorry, that is equal to minus 10 times, you increase the power, so it's going to be, and then you divide by the new power. I'll put the plus c in a second. So then the 2 is going to go up on top, and that's going to be 3, so that's going to be minus 115 u to the 3 over 2, and that's going to be plus c. And again, you can either change the limits at the beginning, or you can then rewrite this as that's minus 1/15, and then your original u function was 10 cos x minus 1, and then that would be to the power of 3 over 2. And then you wouldn't need the plus c if you were going to sort of substitute in pi by 3, 0. The only thing I would have to stress about this when you're putting it in for trig functions, you're going to have to make sure that that's in radians. Okay, so pi by 3 and 0 will be needing to be in radians. Here's another one which is very similar. I'll write this out and then sort of put it in for you, but it comes out to be in u to the half again. So when you've got these notes, you will see that that would be already written as down for you, but I'm going to skip on to the next question only because I am aware of time. So use the substitution that x equals 4 sine theta to show that this is actually b sine squared theta. Okay, so if we have, I know it's a strange one, but these, if you think sine to the minus 1 is differential of sine to the minus 1 is in your formula booklet, and it goes to 1/√1 minus x squared. So I mean, it does then, that 16 minus x, the 1/√16 minus x squared on the bottom does look like it can sort of then go. So how you would go about doing this, again, if we've got our x equals 4 sine theta, so if we do dx by d theta, we will have differential of sine goes to cos, so it's going to be 4 cos theta. X squared is 4 sine theta squared over the square root of 16 minus 4 sine theta all squared. And again, the integral, the limits don't worry too much about. And this is with respect to x. 4 sine theta all squared is going to give me, well, 4 times 4, that's going to be 16 sine squared theta over 16, so the square root of 16, and this is also minus 16 sine squared theta. If you remember from trig identities, okay, so if you remember from trig identities that 1 minus sine squared theta equals cos squared theta, or in this case, if you times it all by 16, you can then write, by the way, this is with respect to x, and I'll go back to that original color. You can then write this is equal to 16 sine squared theta over the square root of 16 cos squared theta, and instead of dx, which is we've got here, this is for cos theta d theta, for cos theta d theta. So if we go to the next page, we will have the square root, sorry, not square root, 16 sine squared theta. The square root of 16 cos squared theta is 4 cos theta, and this is multiplied by 4 cos theta d theta. They cancel out, so you're left with the integral of 16 sine squared theta d theta. What you would then need to sort of do to integrate that is you would have to change that sine squared theta. It was sine squared theta on the top, wasn't it? Or wasn't it sine? Yeah, you're going to have to use the double angle formula to change that from that so that you can integrate it. So you can't integrate sine squared. You'd use one of the double angle formulas, maybe 2 sine theta cos theta. No, not that one. I can't remember at the moment off the top of my head, and my notes aren't there. Okay, so I'm going to move on very quickly to this one. I'll fill that a bit in. So the height x meters of a column of water in a fountain display satisfies the differential equation dx by dt equals 8 sine 2t over 3 root x, where t is the time in seconds after the display begins. Solve the differential equation given initially the column of water has 0 height. So that means when t is 0, h is also 0. So with this, you're going to have to split the differential equation. So we've got dx by dt equals 8 sine 2t over 3 root x. So the 3 root x goes with dx and the 8 sine 2t goes with dt. So we have 3x to the half dx equals, now we can integrate this side, 8 sine 2t, and we can integrate this side with respect to t. In doing so, we have 3x to the 3 over 2 divided by 3 over 2 equals 8 sine 2t. Sine goes to minus cos, and then the 2 would come out, so it'll be 2 too many, so it's going to be 8 over 2 minus 8 over 2 cos 2t plus c. We have to find out what that c value is, and how we would do that is we would put t is equal to 0, and we would also put x is equal to 0. So in tidying this up, the 3 divided by 3 over 2 is going to be 2x, if I put a line down here, is going to be 2x 3 over 2 minus 4 equals, sorry, minus 4 cos 2t plus c. So C equals 2 times 0, 3/2, plus 4 times cos 2, 0. So then C is equal to 4. So the differential equation that we want is 2x to 3/2 equals 4 minus 4 cos 2t. Okay. Thank you very much for listening over the last 4 weeks. We really hope that you've enjoyed it and that you've got something from it. Today's the last one, and all of the notes and everything that we've done will be sort of put on the website, and it'll also be given to you in school. It's going to be sent to your school, so hopefully you get to see them then as well. Thank you very much, and hope to sort of do this again for you. Goodbye.